Hi guys, this is podcast 4A. We're going to talk about kinetics and collisions in this podcast. All right, first let's just discuss what kinetics is. Kinetics is the study of the rate at which a chemical process occurs, so how fast it occurs. Spontaneous reactions are reactions that will happen, so any spontaneous reaction is going to happen eventually. We just don't know how fast. So an example would be diamond. Diamond will spontaneously turn into graphite eventually. So we can study kinetics to figure out how long this process takes. Kinetics also gives us other information, such as gives us some information about the reaction mechanism, which is exactly how a reaction occurs, exactly what atom is interacting with which other atom. Okay, here's a little outline about everything that we're going to learn about in kinetics. Reaction rates, that is going to be how we measure the rates. Rate laws are how the rate depends on the amount of reactants. Integrated rate laws will be how to calculate the amount left or the time to reach a given amount. And then we'll also apply kinetics to half-life. The Arrhenius equation is going to show us how the rate constant changes with temperature. And then we'll have mechanisms finally, which will be the link between rate and molecular scale processes, exactly how this happens and why it takes as long as it does. All right, there are a couple of factors that affect reaction rates. Just let me remind you that a rate is how fast a reaction proceeds, how fast a reactant turns into a product, and that's something that we will have to determine how to do experimentally. There are a couple factors that affect reaction rate. Concentration is the big one. So as the concentration of reactants increases, so does the likelihood that the molecules will collide. Temperature. At higher temperatures, you know that molecules have more kinetic energy, they're moving faster, and therefore they're going to collide more often and with greater energy. Catalyst also can affect reaction rates by speeding the reaction, and it does this by changing the mechanism or how the reaction actually works. And then increasing the surface area by making smaller particles means a faster reaction because you have more things in there and more likelihood they'll hit and actually react. So basically, everything is governed off this collision model. And the collision model just says basically molecules must collide with one another to cause a reaction. But only a small fraction of collisions actually produce a reaction. Why do you think that is? Well, first off, collisions must have sufficient energy to produce the reaction. So the energy must be either equal or exceed the activation energy for that reaction. And the particles that collide must be correctly oriented with one another in order to ensure that a reaction occurs. So here we see, this is a diagram. You have fraction of molecules on the y-axis, and then you have down below, I don't think you can see it, is the kinetic energy of the molecules. And this is a kinetic energy diagram, basically. The dotted line is the activation energy, and that basically is the energy that we have to overcome in order for a reaction to occur. And we see that as the temperature increases, the fraction of molecules that can overcome the activation energy barrier also increase. Okay, so here you have a lower temperature, and here you have a higher temperature. So you see that you have a larger fraction of the molecules can actually exceed or reach the activation energy with a higher energy than when you're at a lower energy. Another thing to keep in mind with this is that this activation energy barrier, if you were to talk about how a catalyst might change your reaction, you would want to actually move that activation energy barrier. Okay, so if you were going to show where a catalyst would come in, you would actually just draw another activation energy line just going up through here, okay? So this would be like your second activation energy, so maybe EA2. Okay, another thing to consider is when you're comparing low versus high temperature, see how at high temperature you have a broader curve, so it doesn't go quite as high, but it's fatter also. okay, which means more molecules reach over here. Another thing to note is that the areas under these little curves right here, this and this part, are equivalent to each other. They will always be the same because they represent the number of molecules in the sample. So they'll always be the same number no matter what. We're just talking about different fractions with different kinetic energies. Okay? If you were to increase the concentration of reactants at, say, the high temperature, the only thing that you would see change on the activation energy or the kinetic energy plot here is you would just see a bigger hump with the same shape. Okay, so that would just represent a higher concentration right there. All right, so this is a picture of a reaction coordinate diagram. It is a very helpful diagram that will help you see the energy changes throughout a process. All right, so let's just start learning these. So these are a little different than the kinetic energy diagrams. Here you have potential energy on the y-axis over here, and then you have the reaction coordinate at the bottom. So reactants are always the first part, and products are always the second part. This diagram is going to show us the change in energy of the reactants and the products, okay, which will also allow us to see the overall change in energy. So from where the reactants are to the highest point, that's going to be called the activation energy. That's the barrier we have to overcome. So here you see it in the green. Basically, it's telling us that there's a minimum amount of energy that is required to break the bonds and make new ones. So it's like this little golf picture. You have to have enough energy of your golf ball to get over the hill to make it to the hole. So same thing with reactions. They have to collide with enough energy and with the correct orientation so that they have enough energy to actually produce a reaction. Okay? All right, in this next picture, you see that the very top part is called the transition state. Okay, so that's when you have kind of a mixture of a reactant and product, and that mixture is often termed the activated complex. Okay, and the difference in energy between the reactants and products is going to be your total change in energy for the entire reaction. So here we have a little example. We have 2BRNO is going to be producing 2NO plus Br2. And you see at the top we have kind of a mixture of the two. This is the activated complex at the transition state. So that's what's occurring when we're reaching the activation energy barrier. All right. I did want to make a little note about endothermic versus exothermic reaction pathways. They do look a little different. Exothermic, you see that your reactants and your products, there is a excess of energy, okay? So this is where you started and this is where you're ending. So you have an excess of energy. You have extra energy here, okay? So say you started at 20 and you're ending at 5. That means you have 15 extra kilojoules of energy here. So extra equals exo. All right, endothermic, you have exactly the opposite. Your reactants have a lower potential energy than your products. So the difference between them is you're losing energy. Okay, so if you start at, say, 5 and you're ending at 20, that's a loss of 15 kilojoules per mole. Okay, so you're having to input 15 kilojoules just to get this reaction to reach completion. Okay, so that is important to note when drawing reaction pathways and reaction diagrams. All right, so in this example, we are asked to draw a potential energy curve. And you see in this potential energy curve that we need to have an energy of the reactants be 30 kilojoules. So we're going to go ahead and write in the reactants right here. All right, the next thing that we're going to need to look at is that the delta H is 10. That means the difference between the reactants and products is an increase of 10, which means there should be, the product's energy should have 10 less than what the actual reactants had. So if the reactants were 30, that means that the product should be 20. Okay? All right, next thing we have to look for is the activation energy. It says it should be 25, so that means we need to increase from our reactants all the way to 25 and then all the way back down to our products. So 30 plus 25 gives us an activation energy of 55 total. Okay? And that allows for the difference between our reactants and products from 30 to 20 to be the difference of 10, which gives us the overall change in our reaction. All right, so just getting back to the general idea of kinetics here, remember that we're studying rates, and a reaction rate is defined as the change in concentration over time. So here in this little simulation below, you see that initially you just have this A and this BC, which is what's being added in equal amounts at the beginning, and we're trying to form this AB and this C. And you see that we're starting at a low temperature, and you see that here's our reaction coordinate diagram. So at this point, we're not producing enough energy to get anything going on. Okay? Now, as time goes on, the temperature will eventually be increased, and when the temperature is increased, you can see that, see here, there's the increase in energy. You can see that the total average energy goes up, which means that you start to produce more reactants. Okay, so you eventually start producing more of those ABs and those BCs. I mean those ABs and that C there. Okay, all right. Here we have an equation. We have nitrogen plus hydrogen gas is forming NH3, and we see that over time, hydrogen gas, which is a reactant, that the concentration of it's going down. So it's reacting and it's forming something else. We have less of it. Okay. In 2, you see that it is also decreasing over time. It has a lower stoichiometric ratio though, so it's not going to decrease nearly as fast as that hydrogen. And then you see that the NH3 goes up as the products, or as the reactants, the N2 and the H2 are going down. Okay, so we're producing the NH3, so it's going up. Okay. All right, so to calculate rates, we're going to take the average rates are taken over long intervals, and then we have instantaneous rates, which are determined by finding the slope of a single line tangent to the curve at any given point. Okay, and then lastly, we can do the derivative. All right, so here's the first one. So this would be taken at average. So remember that slope is y2 minus y1 over x2 minus x1. Okay, so in this situation, y2 would be, let's see, probably about, say 1.8. So 1.8 minus, got y1, say about 3.4. Okay, over x2 minus x1. So our x here is probably a little over 3, so we'll say 3.2 minus our x1, which is probably about 0.6. Okay, so we have that 1.8 minus 3.4 over 3.2 minus 0.6. All right, and we see that that is negative 0.62. Okay, so that would be the average rate. Okay, to move on to the instantaneous rate, you're just taking basically the slope of the line at that point. So you just really want your y over your x. So you've got about 2.5 over your x, which we'll call about 1.7. So you got 2.5 over 1.7, which gives you about 1.5. So you see those are very different slopes, okay? And we also know it's negative because of its direction. All right, now the last method, so that would be our instantaneous slope. And for those of you that know a little about calculus, you know that if you take the slope of a tangent line limitless number of times, you can actually find the derivative of the line, which will give you the true slope of the line. So that's actually our best bet. But we are a little limited by our abilities at this point.